Good morning. Billy, please read the problem.
Flippin' physics.
A 55-gram mass is attached to a light string, which is placed over a frictionless, massless pulley and attached to a 199-gram block, which is on a board inclined at 39.3 degrees as shown. Assuming the block starts at rest and the coefficient of kinetic friction between the incline and block is 0.38, how long will it take the block to move 13 centimeters?
Thank you, Billy. Bobby, please list all of our known values and what we are looking for.
Okay, we have two masses we need to be able to tell the difference between. So let's label the mass which is hanging from the string as mass 1, and the block on the incline as mass 2. That means our known values are mass 1 is 55 grams, mass 2 is 199 grams, the coefficient of kinetic friction is 0.38, the incline angle theta is 39.3 degrees, the displacement of the block in the parallel direction is 13 centimeters, and change in time equals question mark.
Thank you, Bobby. Bo, what do you think we should do now?
Let's draw the free body diagram. There are two objects, so now we have to draw two free body diagrams, right, Mr. P?
Yes, Bo, we now have two objects on which we need to draw free body diagrams.
All right. Mass 1 has a force of gravity acting straight down on it, force of gravity 1. Mass 1 also has a force of tension acting on it, straight up on it, force of tension 1. Mass 2 has a force of gravity acting straight down on it, force of gravity 2. There is a normal force on mass 2, which is up and perpendicular to the incline. Mass 2 also has a force of tension acting on it caused by the string, so that force is parallel to and up the incline, force of tension 2. There is a force of kinetic friction acting on mass 2. However, is it up or down the incline?
That is a great question, Bo. In order to figure that out, who can remind me of the three things I asked you to remember about the direction of the force of friction?
The force of friction is always parallel to the surface causing the friction.
It opposes motion.
And it is independent of the direction of the force applied, right?
Those are all correct. And clearly the direction of the force of friction is independent of the direction of the force applied. There is no force applied in this problem. Okay, so we can see the force of friction is parallel to the incline, so as Bo said, it is either up or down the incline. The way we determine which direction the force of friction is acting is by determining which direction the masses are moving.
But the problem does not tell us which way the masses are moving, so what do we do?
At this point, let's predict which way they will move and solve the problem. I'll talk more about this step later in the problem. So, which direction do you think mass 1 will move, up or down?
I think mass 1 will go down.
I agree. Mass 1 will move down.
Actually, I think mass 1 will move up. I think mass 2 will pull mass 1 upward.
Well, let's go with the majority. Our prediction is that mass 1 will go down and mass 2 will go up the incline. That means the force of kinetic friction will oppose that motion and be parallel to and down the incline. Now that we have identified the direction we think the objects are going to move, let's add that as a positive direction to our drawing. The pulley changes the direction of positive motion from up the incline to down at mass 1. This is a very important step, and you have to be clear to both yourself and the grader which direction you have identified as positive. That is what the positive direction arrow on the drawing is for. Okay, we need to talk about the two different forces of tension. Please realize, because the pulley is massless and frictionless, those two forces of tension, force of tension 1 and force of tension 2, are equal in magnitude. If the pulley had mass, the two forces of tension would not be equal in magnitude. If the pulley were not frictionless, the two forces of tension would not be equal in magnitude. Do not worry, pulleys will have mass and friction in later problems, but not yet.
Great.
Thanks.
Thanks.
Okay, Now I am going to replace all of those capital F with a subscript variables with different variables. Force of gravity I am replacing with a capital W for weight. Force of tension I am replacing with a capital T for tension. Force normal I am replacing with a capital N for normal. And force of kinetic friction I am replacing with a lowercase f with a subscript of K for force of kinetic friction.
Why?
Valid question, Bo. While I prefer every force to be labeled consistently with a capital F for force, and subscripts identifying what kind of force, there are other correct ways to identify all of these forces, and these are all examples of other letters that are sometimes used to identify them.
Why?
Yeah, if you prefer it the other way, why are you doing this?
Yeah.
Because you need to get used to seeing and using other variables sometimes. Mine are not the only ones you are going to see.
Okay.
Yeah.
Sure.
All right, so we have listed our knowns and what we are looking for. We have drawn two free body diagrams. We have identified the direction we think the masses will move and added that positive direction to our drawing. Let's now break force of gravity 2 or weight 2 into its components. Previously, we have derived equations for those, so all we have to do is redraw the free body diagram with the components of the weight. Now what do we do?
Sum the forces?
Why?
I'm not sure, but I cannot think of anything else to do.
We use Newton's second law to sum the forces and solve for the acceleration of the system. The acceleration will be constant, so we can use a uniformly accelerated motion equation to solve for change in time.
Right, Bo, that is correct. But realize we now have two different objects. So when we sum the forces, we need to not only identify the direction we are summing the forces in, but we also need to identify which object or objects we are summing the forces on. Okay, Billy, please begin using Newton's second law and sum the forces.
Okay. We need to identify the object or objects we are summing the forces on and the direction.
You could sum the forces on mass 1 in the positive direction.
Or you could sum the forces on mass 2 in the positive direction.
Or you could sum the forces on mass 2 in the perpendicular direction.
Or you could sum the forces on both masses in the positive direction.
Wow.
Yeah.
Exactly. Lots of choices. Billy?
Okay. Let's do the last one Bo said. Let's sum the forces on both masses in the positive direction. That equals, well, weight 1 is positive. Force of tension is up on mass 1, which is negative. Force of tension is up the incline on mass 2, which is positive. Those two tension forces are equal in magnitude and cancel one another out. Force of kinetic friction on mass 2 is down the incline, which is negative. And force of gravity parallel on mass 2 is down the incline, which is also negative. That is all the forces in the positive direction acting on both masses. Net force also equals mass times acceleration. We can now substitute mass 1 times acceleration due to gravity for force of gravity 1. Substitute the coefficient of kinetic friction times force normal for force of kinetic friction. Substitute mass 2 times acceleration due to gravity times sine theta for force of gravity 2 parallel. And again, that all equals mass times acceleration.
Billy, this is good so far. However, we are missing a bit. Who can tell me what this equation is missing?
Oh, I see it. Okay, so the mass times acceleration part needs subscripts.
Oh.
Yeah.
We summed the forces on both masses, so this is the total mass, and it is the acceleration in the positive direction. Let's call that acceleration parallel because it is parallel to the motion of the system. That acceleration parallel is the same for both masses because they are attached by the string. That means we need to also substitute mass 1 plus mass 2 in for total mass at the end of the equation.
Very nice, Billy. Bobby, please tell me what variables we currently know and do not know in this equation.
We have values for mass 1, acceleration due to gravity, the coefficient of kinetic friction. We do not currently know the normal force. We know mass 2, and again, we know acceleration due to gravity. We know the incline angle theta. Again, we know both masses, but we do not know the acceleration in the parallel direction. So we know everything except the normal force and the acceleration of the system. That means we need to put this in our
Equation holster.
That's right. We put that equation in our equation holster for later use. But what do we do now?
We sum the forces again. From our holstered equation, I know it would be helpful to determine the normal force. So let's sum the forces on mass 2 in the perpendicular direction. That equals positive normal force minus weight 2 perpendicular, and all that equals mass times acceleration. Oh, sorry, mass 2 times acceleration in the perpendicular direction. Mass 2 does not move perpendicularly to the incline, so its acceleration in that direction is 0. The normal force then equals weight 2 perpendicular, which equals mass 2 times acceleration due to gravity times cosine theta.
Actually, Bo, please keep going and determine the acceleration of the system.
Sure, substitute the equation I just got for the normal force into the equation we just holstered. Then we can solve for the acceleration in the parallel direction, which is the acceleration of both masses because they are connected via the string. When we substitute in numbers, we get 55 times 9.81 minus 0.38 times 199 times 9.81 times...
Wait a second, Bo. I think we need to convert the masses to kilograms because kilograms are the base SI unit.
Actually, we do not need to this time because the units for mass are in every term in the numerator and every term in the denominator of the fraction, which means the units for mass will cancel out in this equation.
Billy, you are correct that the units for mass will cancel out in this equation, and therefore we do not technically need to convert all the masses over to kilograms. However, I actually suggest that we do convert them because it is a good habit to get into. Bo, continue please.
Yeah, so 0.055 kilograms times 9.81 minus 0.38 times 0.199 kilograms times 9.81 times the cosine of 39.3 degrees minus 0.199 times 9.81 times the sine of 39.3, all divided by the quantity 0.055 plus 0.199, and that equals negative
5.00390 meters per second squared.
Negative acceleration?
Yes, we got a negative acceleration. Right.
Yeah.
What does a negative acceleration mean in this example?
It means we picked the wrong direction. I knew I was right. The block moves down the incline, not up the incline.
Yeah.
I was right.
Okay.
So all we need to do is change the acceleration to positive and we can keep going.
I do not think we can do that.
Why not?
I'm not sure. It just does not feel right.
Because the force of friction is in the wrong direction. Now we know mass 2 is moving down the incline, so the force of kinetic friction is actually up the incline.
So do we need to reverse the positive direction and redo everything?
We could do that, however, we do not need to. We can leave the direction we identified earlier, however, we do need to change the direction of the force of kinetic friction.
Oh, so we just need to change the force of kinetic friction to positive in the net force equation, and that positive carries all the way through to the acceleration equation with all the numbers, and gives us hold on, just give me...
Negative 0.483741 meters per second squared for the acceleration of the system in the parallel direction.
Correct.
Yeah.
Now, just to make sure y'all fully understand this, Bobby, please explain what it means that the acceleration of the system is negative in this example.
It just means the acceleration of the system is opposite the direction we picked as positive and identified in our drawing. In other words, mass 1 is accelerating upward and mass 2 is accelerating down the incline. That's all it means.
Correct, Bobby. All right, We are getting close to knowing how long it takes for the system to move 13 centimeters. Bo, please determine that.
Okay. We have the acceleration. It equals a number. So the acceleration of the system is constant. Therefore, we can use a uniformly accelerated motion equation. We are looking for a change in time, and we have the displacement. So let's use the original form of the equations. Let's use displacement equals velocity initial times change in time plus 1/2 acceleration times change in time squared. It starts at rest, so the initial velocity equals 0. Multiply through by 2. Divide by acceleration and take the square root of the equation to get change in time equals the square root of 2 times displacement all over acceleration. With numbers, that is the square root of 2 times, well, we need the displacement in meters, not centimeters, so 0.13 meters all over negative 0.483741. That works out to be, hold up. We cannot take the square root of a negative number. We did something wrong.
Yep.
It's the displacement. We got the direction of the displacement wrong. The displacement is negative 0.13 meters. It's negative because the system moves 13 centimeters in the negative direction.
Yep. Bo?
Okay, then the change in time equals 0.733129, or 0.73 seconds with 2 significant digits.
Awesome. It took a bit, however, we got to the answer. Now let's see if the physics works.
Mr. P,
Yes, Billy?
if the two masses are supposed to accelerate, then how is it that they are at rest on the incline?
Yeah.
Okay. I think you are asking, how could the system be at rest at this angle, but also accelerate at this angle, right?
Yeah.
Sure. Does anyone remember how the coefficients of static and kinetic friction for two surfaces are related?
Oh, right. The coefficient of static friction is always greater than the coefficient of kinetic friction for the same two interacting surfaces.
Right. So the coefficient of static friction here must be large enough to hold mass 2 in place. However, the coefficient of kinetic friction is not large enough to stop mass 2 if it is already moving. Nice one, Mr. P.
Thanks.
But how are you going to start mass 2 in motion but not give it an initial velocity?
All I have to do is give the incline a gentle tap. That will cause the two surfaces to vibrate relative to one another and switch from static to kinetic friction. However, it will not give the system an initial velocity.
Cool.
Nice.
Sure.
Here we go.
0.73 seconds. Very nice, Mr. P.
All right.
Yep.
The
physics works. The physics works. The physics works. The physics works. The physics works.
Okay, now, I do want to point out that we could have determined which direction the system was going to accelerate before we summed the forces on both masses in the positive direction. Look at the free body diagrams, and I will remove the force of kinetic friction for a moment. Tell me what you see.
Oh. We could compare the magnitude of weight 2 in the parallel direction to the magnitude of weight 1.
Right. The forces of tension are internal to the system and cancel one another out.
So if weight 2 in the parallel direction has a larger magnitude than weight 1, it will accelerate down the incline. If weight 2 in the parallel direction has a smaller magnitude than weight 1, it will accelerate up the incline. That makes sense.
So we could have done that instead of guessing which way the system was going to accelerate?
Yes,
I think I'll do it that way next time.
that would be an equally valid way to solve the problem, Bo. Now, I also want to review a couple of new things. We still have the same 5 steps to help solve any free body diagram problem. Bobby, what are those?
Draw the free body diagram, break forces into components, redraw the free body diagram, sum the forces, and sum the forces in a direction perpendicular to the previous direction.
Right. We still have all those steps. However, please notice that we can sum the forces more than twice now. In this problem, we could sum the forces on mass 1 in the positive direction, mass 2 in the positive direction, mass 2 in the perpendicular direction, and the whole system in the positive direction. You have to look at the situation and determine which of the possible object or objects to sum the forces on, and which direction or directions to sum the forces. And remember, you need to identify both the direction and the object or objects you are summing the forces on. Thank you very much for learning with me today. I enjoyed learning with you.